let's talk about rotations as far as kinematics go, so motion. And before we do that, let's kind of put in perspective what some of these measurements actually are. And I have a marker everywhere. And the first one that I have is like, okay, so how do we figure out what this x distance is? Because if you remember when we did kinematics with linear motion, let's see, what did we have? We had, we could look at v final squared equals v initial squared plus 2a delta x. That was one of them. Or we could go, let's see, x equals the initial velocity times time plus 1/2 at squared. Let's see, and we also just go with the common one that, let's see, v final equals v initial plus at. And then I remind everybody that this is just the definition of acceleration, right? So final minus initial velocity, that's a change in velocity. A change in velocity over time gives you acceleration. So this is just this thing rewritten. And this one, well, without acceleration, well, this is just rate times time equals distance, right? So all of these things are pieces that we've been dealing with, but now we're going to have our things rotating. So we've done, let's see, the forces required to make something rotate. We've done center of mass. We've done the moment of inertia. And so now we can start talking about like kinematic equation, kinematic pieces related to this motion. All right, so the first thing I said is, so how do we relate this distance? Like if I wanted to get this x here, kind of thinking in terms of our linear pieces. Well, here I have a circle. And if I drew a really good circle, you'd be able to tell that this is like 1/4 of the circle. So let's see, so that would be like 1/4 of the circle, 1/4 of the circumference. So this distance then would be that. Let's see, and circumference, remember this is 2 pi, is taking a whole trip around here. And because this just gives us a ratio, it says however big this radius is, I can get to this entire distance around by relating the radius to that ratio 2 pi. So I have 1/4 of my circle times this 2 pi r. And then I can simplify this further and I can go like, so x is, let's see, what is this? This is actually pi over 2 times r. And so let's think about what this piece means. What is this pi over 2? Well, hopefully this kind of looks like a 90-degree thing, right? And that's exactly what this is. This is an angle theta. And at 90 degrees, let's see, 90 degrees is pi over 2 radians. So this thing here then is just saying we can define our displacement in terms of this angle theta and the radius of that circle. Pretty cool. I want to emphasize to you that everything we're going to be doing now is not in terms of degrees, but it's going to be in terms of radians. So this theta here is in terms of radians. Now let's think. So we have a change in velocity over time, and that velocity is, let's see, a change in position with respect to time. So a change in position with respect to time. So if x is a theta r, so a change in theta r is my x divided by time. So this piece, what does this give me? If I think about that one, well, what I can say is that if I want to think strictly in terms of not velocity, because that's what this is, right? I've defined that. This whole thing would be changing rotational motion to velocity. So what I actually have, if I look at this piece, this gives me how quickly this radial rotation is happening. So how quickly am I going through my unit circle per unit time? So let's see, so we'll have this thing that we'll define as theta, and theta is then the change in that, or I'm sorry, omega. That's theta, that's omega. So omega is going to be the rate of change of our radii, I'm sorry, of our theta with respect to time. And now over here we had A, and so what we use is this kind of fish looking thing that's called alpha. And just as acceleration is a change in velocity with respect to time, our alpha is going to be a change in omega with respect to time. So can we relate these things then back to our linear displacements? So we've done this for x, and I've kind of done this for omega. So to go from v, or actually let's go from omega to v, what did I say? I said, so this is our omega piece, and this here was my x piece. So omega times radius, omega times the radius gives me velocity. Let's just put a box, not a dash circle around that. So I have my x in terms of theta, so my rotation, and I have a velocity in terms of omega. So the last piece here then is omega, I'm sorry, is alpha to, how do I go from alpha to acceleration? Where this would be tangential acceleration. I should be clear about that. Let's see, so if omega times r gives me velocity, then alpha, which is in terms of a change in omega, times r will give me tangential velocity. Acceleration, sorry about that. Cool. So now the last thing that we can do is put these pieces in terms of our rotational kinematics. This is the thing that we're going to be using for a bit. Rotational, rotate. We'll just start that word over. I don't know what happened there. Rotational. There we go. Kinematics. So we have stuff like that. What about this? If I replace b, or what velocity, with omega, so I'd get omega final equals omega naught plus alpha t. Oh, so it's just kind of feeling like I'm just kind of replacing these things, and indeed I am. That theta equals theta naught plus omega t, omega naught t, plus 1/2 alpha times squared. And that's how they all rock. So this is delta theta, or d theta, which is the same as, this is actually, if I was being complete, that's a change in x. So this is a change in the theta, is omega t plus 1/2 at squared, alpha t squared. And I can do the same thing with this, that I can go omega final squared equals omega naught squared plus 2 alpha delta x, delta theta. So these guys, that's the nice thing, something that you're used to working with, gives us the exact same thing in rotational kinematics. The only difference is we have kind of these bridges that can get us from our different linear behavior to our rotational behavior. And now we're going to play with that for a second, or actually more than a second.